Hola.
Obrigado por nos hospedar. Bem-vindo. So, I'm sorry, that's all the Portuguese I speak. Welcome. We call this talk A Brewer's Guide to Filtering Out Complexity and Churn. We also call it the Coffee Machine Talk, and you'll see why. Our goal here is to show you how to remove from your applications the bitterness that's caused by complexity and churn. Over the next 30 minutes, we'll show you how complexity will sneak into your code base, how to recognize it before it becomes painful, and how to remove it permanently. So we're going to introduce ourselves, and then we'll get going. I'll go first. Hola. I'm Alan. I have about 13 years of experience with Ruby. I'm from Seattle originally, where Starbucks was born. So there's coffee in my veins. My favorite is a sugar-free vanilla oat milk latte.
Hola. I'm Fito. I also have 13 years of experience with Ruby and Rails. I'm actually originally from Asunción, Paraguay, but I've been in the San Francisco Bay Area for the last around 13 years or so. And if there's one thing I love as much as I love Ruby, is coffee. My favorite is a Ghirardelli dark chocolate mocha. If you're ever in the San Francisco Bay Area, get one. They're delicious. Now, Alan and I work together at a company that you might not expect, given that this is a conference for Rubyists and people who use Rails. We work for Cisco Meraki, and it is the largest Rails shop you've never heard of. But we've also been friends for years. In fact, we've worked together over the last 10 years at 3 different companies, and we've seen a wide variety of code bases of different sizes. And we spend time on the weekends just writing code and drinking coffee. Alan, you grew up around coffee, didn't you?
Yeah, I did. In fact, when I was a kid, nothing fascinated me more than these mechanical coffee machines. You would drop in a coin, listen for the clink, make your selection, and the machine would just spring to life with hissing and clicking and whirring. And when the whole thing ended, that final sound that you would hear was that glorious aromatic black liquid splashing into the cup. Magnifico. These days, I'm more fascinated by the inner workings of software. We both are. And like that coffee machine, there are all kinds of hidden complexity in code. But it doesn't start that way, does it? Show of hands, how many of you have worked on a greenfield or a brand new application? Wow. How did that feel? A pleasure, yes. Now, how many of you have worked on a legacy application? Even more of you, yes. And how did that feel? Yeah. Why is that? Well, we believe that it has to do with complexity. That at some point, code bases cross a threshold where after which you really only have 2 choices. You can either live with the complexity as it grows and grows and development slows down more and more under the delusion that it will go away on its own, or you can pause temporarily, reflect on the design, and reorganize the code to accelerate development again. And we've seen organizations go both directions, and invariably, when you take that first path of living with the complexity, engineers end up frustrated. And in our experience, it sometimes even gets to the point where people begin to blame Ruby and Rails. And they start looking for alternatives. But it's not Ruby's fault. It's not Rails' fault. It's that complexity. So what we're going to show you how to do is to take the second path. Remove the complexity and fall back in love with Ruby and Rails. So we're going to build a little coffee machine. We'll add several features, then we'll go back and look at the complexity, how it snuck into the program with each commit, and finally we'll reorganize the code to be able to add new features without increasing the complexity. Are we ready? Okay, let's get started. Fito, do you want to build a little coffee machine?
Yes, let's do it. All right, so how does complexity get into software? And the answer, of course, is one commit at a time. It kind of sneaks its way in. So we're going to take a look at that. Now I'm going to move through the slides pretty fast just to show you the shape of the code as it grows. And as the code gets longer, the font size will get smaller. So don't worry about trying to understand the actual code is made up anyway. Also, we're skipping tests here, but in reality, we would not be doing this without tests. Just for the sake of time, we won't be writing them. All right. Here is the first commit in our coffee machine. At this point, the machine does one and only one thing. It serves coffee. First, it's going to dispense a cup, then it heats the water, it prepares the grounds, dispenses the hot water on top of it, and then finally, it disposes of the ground. Now, this works great, but we get feedback that not everyone likes coffee. So to increase our sales, we're going to add tea. All right, here we added a conditional to determine whether to serve coffee or tea. And in the process of doing that, we introduced some duplication here. The calls to dispense cup, heat water, and dispense water steps are all duplicated between the two beverages. So naturally, at this point, you would dry it up. Here's the dry version of the code. All right, and now that we have coffee and tea in production, we're starting to get feedback. The most frequently requested feature is, can we add sweetener? So let's do that. All right, here we've added sweetener just after dispensing the hot water. Of course, not everyone wants sugar, so we're gonna make it an optional ingredient. Okay, we push this out, customers like it, and now they want cream or milk. And we already have a pattern here for optional ingredients, so let's just dispense the cream right after we dispense the sugar, also optionally. Okay, we push this up, customers are liking it, and then for the next feature, it turns out that some folks don't like either coffee or tea. So we're gonna offer them something else like cocoa or hot chocolate. Okay, here we follow the existing pattern and we added cocoa to the main if statement. But there's no need to add milk or sugar since the cocoa powder that we're using to make our cocoa is already sweet and creamy. So we're gonna exclude those optional ingredients when the customer is requesting cocoa. Right, and finally, who doesn't like whipped cream on their cocoa? Heck, I even like it on my coffee. So let's add it. Okay, so whipped cream is an optional ingredient that no one wants on their tea. So we're gonna add it below the other optional ingredients, and we're gonna exclude it if the drink that was selected was tea. All right, so here we are. We are 7 commits into this little code base, and we've already got 9 conditionals in one method. Now, at this point, it's still relatively simple to understand and to work with, especially if you are the only one working on it. But if you're a part of a team, procedural code like this just does not scale. Future developers will just continue to extend what we have there. They're gonna keep adding more conditionals with each new feature, and the complexity is just gonna skyrocket. And we were moving fast, releasing features. Our little coffee machine has been so successful that it was just purchased by a big national soup chain. And they want us to add soup to our machines. So that's gonna add a lot of complexity to our code. So maybe this is a good point to pause here, evaluate where we are before we try to add any more features. Alan, can you take us through that?
Sure. So we've reached an inflection point in the life of the coffee machine. But how do we know? What is it that tells us to pause and reflect? Well, the first hint is that we had to keep reducing the font size to get the whole method on the screen. Method length is definitely an indicator of how complex something is. Sandy Metz, the author of Practical Object-Oriented Development in Ruby, which if you haven't read, you should go read, has a rule about it. She says methods can only be 5 lines of code, just 5. In addition to method length, we also look at method complexity. Now, this is a quantitative measurement of how difficult it is to understand a piece of code. Our preferred metric is called the assignments, branches, and conditional metric, or ABC. The higher the number you get, the harder it is to understand that code. Now, we use a gem called Flog by Ryan Davis to measure this for us. Now, Flog calculates the ABC score for each method in the application. But how do we know what is a good score? Well, way back in 2008, a man named Jake Scruggs, who wrote the metric food gem, blogged these numbers. And to this day, these are the only references we can find on the internet. But we've used them for many years, and they're actually quite effective at helping us simplify our software. So how does our little coffee machine fare? Let's go back through and look at complexity over time and pay particular attention to those green numbers. 0 to 10 is awesome. 11 to 20 is good enough. So in our first commit, we have a complexity of 5.5. That's awesome. Now the churn number you see here is just the total number of commits to that file. That'll become important later. Adding the conditional with a duplicated code moved the complexity up to 14.6. So we're no longer in the awesome zone, but we're still below 20, so that's good enough. Now, when we removed the duplication, the complexity dropped back down to 10.9. That might seem like a good thing, but this is actually where things start to go wrong. Notice how we've intermingled the two algorithms in a way that it makes it harder to understand how you're brewing coffee or steeping tea. It also sets a precedent for future developers to add additional beverages with more conditional logic. Now, from Flog's perspective, from the algorithm's perspective, complexity went down. There are fewer assignments, branches, and conditionals. It can't tell that we intermingled the algorithms. It's just doing math. This is a valuable lesson because there is no magic metric that can light the way in every situation. Rather, there are tools like Flog that can inform our decision making. So pay attention to how hard it is, how hard it feels to add new features to your application. If it feels like it's slowing down, stop, pause, reflect, and take a look at your design. All right. Next, we added sweetener. That's our fourth change, and complexity is back up to 13.5. We added cream. That pushed it to 16. We're still in the good enough zone. Adding cocoa pushed the complexity up to 21.3, just above the good enough line. Let's see where that last feature puts us. So we topped things off with whipped cream, and that pushed the complexity score up to 25.5. Now, if we look at the trend line, we can see that complexity has reached a point where it's curving upward. Plus, we're way over the good enough line now. So there you go. 3 ways to know when it's time to pause and reflect on your design. First, method length. Just literally, how long is the method? Anything over 5 is forbidden by Sandy. So keep it short. Method complexity is next. Anything under 20 is good enough, and anything over 60 is getting dangerously complex, so you really ought to reflect on those. And then how does it feel? If new feature development is slowing down, it might be time to pause and reflect on your design. So that's how we knew it was time that we'd reached this inflection point. We wanted to start thinking about reorganizing the method before we added more features to it. And so that's what Fito is going to do right now.
So we broke Sandy's rule. We crossed over Jake's good enough line, and we intermingled those 3 algorithms. That all sounds very dire. But is it? Can we turn this around? Yes. We're going to do it right now. All right. So here's a method as we left it a moment ago. Now, code that is dry too early, and there's always that urge to, we see repetition and we're like, let's try it, right? But code that's dried early can often lead us in the wrong direction. So we're going to undry this code or add back the duplication to see if there are any missing abstractions in there that are hiding in plain sight. We call this practice rehydration. But before we do that, it is very important to know here that you can't do any of this without tests. You are going to break your code if you don't have tests. So again, for the sake of time, we won't be writing them right now, but ensuring there's good test coverage is the first step towards reducing complexity. Now, we like this tool a lot. It's called SimpleCoff, and we use it to ensure that we've tested every line and branch of code in our application. So as you can see here, we have 100% line coverage. That's great. We also have 100% branch coverage, which means that we're testing both sides of every conditional in the code. Now, getting to that 100% branch coverage is really important before rehydrating code. It's going to give you that confidence that you're not inadvertently changing the behavior of your code in the process of refactoring it. All right. So this is where we left the code a moment ago. And now we've confirmed that our tests are backing us up. So we're ready to rehydrate it. That would look like this. All right. Obviously, this increases duplication. But that's what we need to do to find those missing abstractions. Now we can clearly see each recipe. And since there's no overlap in the algorithms anymore, we can safely extract each one of these recipes into separate polymorphic classes, like this. Okay, now as you can see, we move each recipe into its own class. Now we have one for coffee, one for tea, and one for cocoa. And this structure has a couple of big advantages. Each algorithm is now separate from the others. That means if you should ever need to modify one of them, for example, you're fixing a bug, there's a much lower risk of you introducing a regression in another one of the algorithms. Plus, the then method now is much simpler. Now, you may have noticed that there's duplication between the classes, right? We just moved that out into individual classes. So the calls to dispense cup, heat the water, and dispense the water are all present in every class. We actually want that duplication. This is what's making understanding the complete algorithms much easier, since the whole algorithm for each beverage is present in each beverage class. So we do not want to dry up the algorithms per se. Rather, what we want to do is ensure that there is only one implementation of each one of those methods. That's really what's meant by don't repeat yourself. It's perfectly okay to call a method multiple times. It's preferable, though, to only implement that method once. Now, Ruby provides multiple options for doing this. We could include a module. We could use composition, like pass in something that implements those. Or we could introduce inheritance and put the methods in a base class. In this case, because we're using polymorphic classes and because we're really unlikely to need these methods elsewhere in the application, we would probably go with inheritance here and put the methods in a base class. All right, we're almost done. There's just two remaining problems. First, the then method has multiple responsibilities. And second, is not really open-closed, meaning that you have to modify the code in order to extend it. For example, when you're adding a new feature. Let's look at the responsibilities bit first. Its only real responsibility should be to prepare the beverage. But right now, it's also picking which class to instantiate based on the user input. So that's the job of a factory. So let's go ahead and introduce one. All right, here we've pulled class instantiation out into a factory class. Its only job is to choose which class to build based on what drink was selected. Now the then method only has the one remaining responsibility, to prepare the beverages. And it is now open-closed, meaning that we'll never have to modify the then method again, even when we're extending the functionality of the coffee machine. The then method now is set to be open for extension, but is closed for modification. However, some of you probably noticed that the open-close problem just moved to the factory, right? And we introduced another sneaky issue here. The build method in the factory might return nil, which is going to cause a undefined method error if we were to get an unknown drink into our coffee machine. Let's solve that first. We can solve it by introducing the no object pattern, like this. So you can see here, the factory returns a null beverage by default. The null beverage class is simply a class with a prepare method that does nothing. Now, it might make more sense to like notify somebody or log it somewhere so we can see what went wrong or what was missing. But the goal is that we're not throwing an exception here. As for the second problem with the factory is that it's still not open close. To add a new beverage, we will have to go in there and add a new conditional. We'll have to modify that factory class. We can solve that by using a different kind of factory. So here, we've replaced the conditional-based factory with one that's based on a convention and a little bit of metaprogramming. Now, the advantage of this approach is that it is mostly open-closed. There might come a day when you want to introduce a class name that doesn't follow this convention, and at that point, we would have to modify the code here, which would violate the open-close principle, right? There are other approaches that are truly open-close, and we would be really happy to discuss them with you offline, but it goes beyond the scope of this talk. So, well, this factory works for our case. Simple enough. We're going to stick with it for now. All right. At this point, I want to go take a look at where we are with our complexity. Let's start here, revisiting this graph that Alan was showing us. Here's where we left off after adding whipped cream. Now, the next thing we did was to rehydrate the code. Oof, look at how much more complex that was than the dry solution. But remember, the dry solution was hiding the fact that there were a missing abstraction in there. So we're going to live with this temporary higher complexity. Now, the next step was to pull the algorithms out into their own polymorphic classes. And now this dropped complexity significantly. And finally, we extracted a factory object. And now the complexity is lower than it's ever been. We are well back in the awesome range, and the Venn method will never need to change again. Now, we create a bunch of little classes, right? So let's take a look at the classes in the app. There are 6. The coffee machine has now settled down to a very low complexity of 3.9. The factory is next at 6.2. And then we have the 3 beverage classes that are a little bit more complex, but they're still well within the good enough zone, so there's nothing really more to do here. Except that there was a reason why we did all that. We needed to add soup to our coffee machine, and we wanted to do so without making it more complex. So here's where we left off. Let's add some soup. There you go. Adding soup did not require us to change any of the existing files. It just works. As long as the soup class is loading into memory, it will be available to the factory. And here's really the goal of this. In the future, adding a new beverage will be as simple as adding another class and its corresponding tests. Let's take a look at that again. So here's the code without soup. And here's the code with the soup. Nothing else changed. Now, I know what you're all thinking probably. This is a very small greenfield application, but your applications are obviously a whole lot bigger and a whole lot more complex than that. So what's the lesson to take away here? How will you know where to start when you get back to work? Alan, can you walk us through it?
Yeah. So far we've really only talked about the method complexity of a single method. But what can we do if we look at the entire application? How can we tell where to begin our journey of simplifying things? It turns out you can use complexity together with churn to sort of give you a map to where to find those problem areas in your code base. Now, as we mentioned, complexity is the measurement of how difficult it is to understand a piece of code, and churn is, by definition, how often you're changing that code. And we like to think of it this way. Complexity is the amount of pain you will experience the next time you touch that file. Churn is how often you are inflicting that pain on yourself. So let's look at how to use churn and complexity together to evaluate the entire code base. So the first thing you can do is to map your complexity and churn on a graph like this. You can use a tool like Code Climate or the Ruby Critic Gem. And this kind of chart was originally proposed by Michael Feathers. He's the author of Working Effectively with Legacy Code, another book I highly recommend. We use this kind of chart to locate the areas in our code base that need an intervention. To understand the chart, let's break it into quadrants and take a look at each one. So the lower left quadrant is the pain-free zone. Files in this area are easy to change and easy to understand. In a healthy application, the majority of files live here. The upper right quadrant is the painful zone. These files are hard to understand, hard to change, and prone to regression. Being aware that these files live in this quadrant will help you make decisions about where to add new code. You probably don't want to add more code to these files. In fact, if you have to touch them, prefer extracting code out of them over adding code to them. This will create simpler classes with low churn scores, because you just created them, and that'll bring them down into that green pain-free zone. Now, down in the lower right are low complexity files that change frequently. It's possible these files are actually just some kind of data masquerading as code, and you can, something like some JSON hiding in an RB file, for example. You can try to move that ever-changing configuration data out of the code. That'll simplify the code, and it'll reduce the churn in that file by not having to change it constantly. And then just read it from a file, just a JSON file or from a database. And then finally, up here in the upper left are the high complexity files that rarely change. These are likely what Sandy Metz refers to as an omega mess. An omega mess is a big file with a scary algorithm in it that really never needs to be changed. And Sandy's advice, and we agree, is that in this case, you should leave these files alone. They're not causing you any pain. They're not changing. So if you get in there and you start to change them, you probably are going to break them unless there's really good test coverage. So just leave them be. Now, these quadrants are helpful to think about, but reality actually looks more like this. Now, the red line represents the pain threshold. Anything in the pink zone will be resistant to change and prone to regression. And this file is in need of the most attention. It is super complex and is being modified all the time. Extracting hidden abstractions from this class will help simplify your entire application. But there's no need to tackle all that complexity at once. Try improving the code incrementally, a little bit each time you touch the file. Also, you might not want to start there. It's super complex code, and maybe you want to start down here. Practice the techniques that we've talked about before you start tackling your most complex code. Okay, that's the story of our little coffee machine, how complexity snuck in, how we recognized it, and how we removed it. We're going to wrap things up with some takeaways and some homework. So first, 3 things we want you to take from this talk. Complexity is going to sneak into your code. It happens one commit at a time, so be vigilant. They could represent objects, pay particular attention to conditionals inside your code. They could represent objects that are trying to escape. And remember, dry is about method implementation, not invocation. As my friend Josh Clayton says, don't make your code so dry that it chafes. Second, you can recognize the complexity before it becomes painful. Keep your methods short, watch your complexity scores, and pay attention to your intuition. If your methods are longer than 5 lines, or your flog scores are over 20, or even if it just feels slower, it might be time to pause and reflect on your design. Third, if you do find yourself in that complex area, you've got pain caused by complexity, you can back away from it. Leverage polymorphism and factories to enable you to add new features without changing any existing files. You can rehydrate your code or reintroduce the duplication to help you find those missing abstractions. All right, those are the 3 takeaways. Now, here's what we want you to do with that information. Go find out what your average method complexity is by using flog. Second, find out which file in your class has the most churn. That's likely a problem area. And third, find out which class needs the most attention. Now, this is the class that has the highest churn and complexity. We think you probably already know which class this is. But go ahead and confirm your suspicions. Finally, let us know what you find. Here's how to reach us. Feel free to write, tweet, or give us a toot. We're actually probably more likely to get an answer if you toot. We're not on Twitter much anymore. You can also subscribe to my blog if you'd like. And if you want to work your way through that code, you can find it on GitHub with tests. Plus, you can check out some of our other projects, including RubyFlog, which is a VS Code extension to show you the flog score for the selected text, the current method, or the average score for the entire class. And that's it. Obrigado.